Hi folks, thank you for joining me. I'm Maurice, Donovan, Senior Technician. I'm a Technical Advisor for TAT and I'm the owner of Allautos Advanced Tuning here in Brisbane. Thank you as we journey on the bus together on the serial bus network systems that are in our modern vehicles for advanced automotive technology. This presentation is directed to the automotive technician and is intended to assist you to be more informed, to be able to help you with your diagnostic skills. Thank you. What is a serial data bus? It's not a product. It's not necessarily a component. Sure, it is made up with wiring and it is an electrical circuit that enables various modules or a diagnostic tool to communicate with each other. So we could say a serial data bus is a vehicle that transfers information from one module to another module or to a diagnostic tool, which is of course our scan tool. But why use a bus? As vehicle manufacturers add more gadgets and emission safety requirements become more stringent, OEMs quickly realise with current wiring harnesses and sensor layouts, using a conventional wiring method would not be possible to manage. Buses help to eliminate wiring and the need for multiple sensors. This is why some components that would not have once been on the serial data bus, such as our lights, wiper motors and even your car radios, are now on the bus. Many different analogies have been used to illustrate the bus network systems. The one I like to use is the one which Jack Sepinen uses when he teaches on data bus networks. He loves to use the choo-choo train. And by using this illustration, he shows the students an excellent parallel to the bus network system. Jack would teach, we have the train track. Serial data has the physical layers, the wires. The train has its stations. Serial data has its modules. The train has its circuits. Serial data has its circuits. The train only stops at the stations that are designated for it to stop at. But it will pass all stations. And all stations are aware that the train is coming, regardless of whether the train stops or not. Likewise, the modules are aware of the message being sent on the bus, but only the designated modules receive this message. Another analogy I like to use is that of a radio broadcasting station. The radio waves leave the station, the waves then travel in the air, and any radio receiver that is tuned to the same frequency can receive the broadcast. The modules that are connected to the bus are tuned to only receive the message that the module is tuned to receive. This is accomplished in the way the start of the message is written. Each module knows which message it is to receive and when it is not to receive a message. It knows this by the identifier that follows the first start frame of each sent message. Let's talk a little about the message. It is all about zeros and ones, or ons and offs. Off is 0 and on is 1. It is that simple, and this is how computers talk. It's called a binary language. Binary means that there is a code of either zeros or ones to which the computer toggles between. It reminds me a bit about Morse code, dots and dashes, or zeros and ones. It's that simple. I suspect the majority of us mechanics, when we think bus, we also think CAN. Let me make this clear. CAN is just one of many different protocols that are written and used in the automotive industry. But before we go into the different protocols, let's just concentrate on the message. As the message is made up of zeros and ones, we only need a 0 voltage and a manufacturer's engineered preset voltage for the bus line. In the automotive industry, we often see 5 volts being the common voltage that is used. But we are now seeing 7 volts and even 12 volts, so it's important to know your system. A message is made up of different sections, so in the same way a choo-choo train is made up with an engine and different carriages and a guard carriage at the end, this is the same for binary messages that have been transmitted on the bus line. The message starts with the starter frame, which is a one single on-off signal, and we call this a bit. Each on-off signal is known as 1 bit. This starter frame is always present at the start of every sent message. It is a wake-up call for the bus that a message is coming. Following the startup frame is the identifier, which is made up of 11 bits, or in some high-level protocols with extended frame format, will have 29 bits. So 11-bit identifier means that the identifier has 11 bits, which includes the first bit known as the starter frame. Maybe a better way to explain the identifier is simply offs and ons, 11 times zeros or ones. I should clarify, a bit is really more of a time-based event, so zeros or ones can be joined together, making the bit a time frame. Therefore, not necessarily an on-off needs to happen for the next bit to start. That means we could have a message 000 1100 1110. So that means we've had 6 dominant off voltages and 5 recessive on voltages, but it has taken 11 bits of time for this to happen. Now, the identifier is one of the most important parts of the message. The identifier communicates the urgency of the message. The more urgent the message, the lower the binary number is, meaning the start of the identifier will have more zeros indicating a high urgency to this message. So an ABS message will no doubt have a much lower binary number than, say, a Windows switch command. This is called arbitration. And always the lowest binary identifier will access the bus line before a higher numbered identifier is allowed on the line. This is pretty cool stuff, guys, and it works really well with very little to no crashes, as all the messages stay in a listening mode until at such times that the bus is clear of any higher ranking messages. No messages are lost, as they just wait until the time is ready for their turn to ride the bus and deliver the message. We can see here we have 3 typical messages that have been sent on the bus at the same time. So arbitration starts. We always start off with a single frame, which is made up of 1-bit wake-up started message, which is seen as a drop in voltage from a recessive 5 volts to a dominant 0 volts. Most protocols use 0 volts as what is known as in computer talk as a dominant command, where a 5 volt is a recessive or an idle command. A dominant is always a higher ranking command, and the more dominant the message, the quicker the message is placed on the bus. Folks, I have read that a certain protocol that works opposite of what I've just explained, where 5 volts is a dominant and 0 is a recessive. I will not worry too much, as this is not the norm, and I somehow do not think we will see this in the types of cars we work on, but I felt I should throw it out there for you. Getting back to the 3 nodes, or as we know them as the 3 modules, that are sending 3 messages to this bus. They are all followed with 2 recessive 5 volt bits, and then 2 dominant 0 volts, followed by a recessive, and then node 1 and 3 follow with a dominant bit. This means node 2 has now lost its arbitration and switched to a listening node. It is now up to node 1 and 3 to determine which module will have the lower number in its message. As we can see, node 3 wins arbitration with the lower binary number. So node 1 now changes to a listening node, while node 3 gets to transmit the important message. Then, if no priority messages have been sent and the bus has become idle, then node 1 switches from a listening node to a transmitting node and will then send its message, followed by node 2. This is how the arbitration works, and it is happening so very quick. It becomes a seamless function that we could never pick up the delay without the use of a high-speed oscilloscope. The bus circuit is a means for serial data to travel. When talking about serial data in a modern car, most of us think of CAN, Control Area Network. CAN was originally designed for the automotive industry and was manufactured by Robert Bosch in 1986, with the first car being equipped with CAN being a Mercedes-Benz 1992. CAN has proven to be a robust, simple and versatile technology. So consequently, CAN is not only used in the automotive industry, but it's also found its way in all manners of household appliances and medical equipment where microprocessors need to communicate amongst each other. Have you ever used a coffee machine in your home or in your office and wonder how the heck it works? Chances are it is a CAN-compliant machine. I want to make something very clear by repeating what I've previously shared with you. Not all automotive serial data run CAN, and not all CAN run the same protocol. We have low speed CAN, medium speed CAN, high speed CAN, open CAN, single wire CAN, and so on. In 2008, the US EPA regulations requiring ISO 15676, part of this regulation was to ensure that CAN standard was to be supported for all US sold cars from 2008 and later. So now we have a standard that new car manufacturers have to use CAN as the main emission control protocol when manufacturing cars today. This doesn't mean that we do not see other protocols being used alongside of the CAN protocol. We now see different serial data protocols being used in all modern cars, and it is not uncommon for the manufacturer to use 3 to 5 different protocols. Before we get too carried away with CAN, let us look at some of these other protocols, these serial data protocols we find in the modern world of cars. Let's start with the protocol UART, meaning Universal Asynchronous Receiver Transmitter. Is an early serial data that GM used and it is a 5-volt serial bus that toggled the voltage up and down. If a module wanted to talk on the bus, it would pull the 5 volts down. It could talk and listen, and it was the first to be bidirectional. UART is still used today. Asynchronous communication means a transmission of data without the use of an external clock signal, where data can be transmitted intermittently rather than in a steady stream. Originally, it was a very slow bus, 160 bits per second. Considering our whole internet dial-up system was typically 7,168 bits per second, and our first CAN protocol had a speed of 125,000 bits per second, really demonstrates just how slow this network was. Do you ever wonder where the U came from in our serial data diagnostic trouble codes? Well, think no more, because it came from this very early protocol, UART. That's right, U stands for UART. So, what is a protocol? In the political world, it would mean the official procedure or systems of rules governing affairs of state or diplomatic occasions. Well, in the world of computers, protocol is also a set of rules that govern an agreed format of transmitting data between two devices. It determines type of error checking and data compression use. It also agrees on a language and an engineer's set speed that the data is allowed to travel on the bus. We simply cannot have one module transmitting at one speed and the receiving module receiving the message at a different speed. The same applies with the language. All modules are part of the same protocol, must all speak the same language. This doesn't mean that other protocols that the manufacturer may have used cannot communicate between the different protocol systems. This is accomplished by the use of a gateway, where the gateway will interpret the different computer languages so all protocols can cross over and function in unity with each other. So let's have a look at some of the different serial data bus protocols we can find in our cars today. We have just taken a short look at the earlier protocol UART used by GM, which first came out in their cars in 1982. Let's start with the protocol BikeFlight. BikeFlight is an automotive data bus created by BMW and their partners to address the need to modernise safety critical functions and a need for a system that would be more fault tolerant when electronic communication between automotive components depended on fast and reliable communication. This is a message-oriented protocol and was a predecessor to the later protocol FlexRay. BikeFlight was first introduced in 2001 and came out in the BMW 7 Series E65. We all know CAN, Control Area Network, which is a multi-master message broadcasting system, meaning that no one module is the master. All modules send messages and all modules receive messages. Therefore, all modules can at times be a master or at other times be a slave. CAN is an inexpensive, low-speed serial bus for interconnecting automotive components. CAN protocol bases its simplicity, such as its message format, message identifiers, and bitwise arbitration is a major benefit and reason for the success of the CAN protocol. Here is a protocol I didn't even know about, D2B, Domestic Digital Bus, which is a high-speed media interface. D2B utilises fibre optic to transmit data and control signals in the form of emitting light signals on the optic bus network. DB2 is used in the Mercedes-Benz model 163 M-Class. We mentioned FlexRay earlier. FlexRay is a general-purpose high-speed protocol with safety-critical features. FlexRay supports high data rate, up to 10 megabytes per second, and is a serial communication technology that is used in particular for data communication in very safe critical use areas in the modern vehicles. The bus operates on a time cycle, divided into two parts, the static segment and the dynamic segment. The static segment is pre-allocated into slices for individual communication types, providing a stronger real-time guarantee than its predecessor by flight and CAN. The dynamic segment operates more like CAN, with nodes that take control of the bus, allowing event-triggering behaviour to be spontaneous. Keyword Protocol 2000, abbreviation is KWP 2000, a protocol for automotive diagnostic devices, runs either on serial line or over CAN. KWP 2000 is a communications protocol used for onboard vehicle diagnostic systems. This protocol covers the application layer in the OSI model for computer network. So what is OSI? OSI stands for Open Circuit Interconnection and is a conceptual model that characterises and standardises the internal functions of the communication systems by partitioning it into abstraction layers. We will talk more on layers soon. The KWP 2000 is a protocol that is standardised by International Organisation of Standardisation, ISO 14230. KWP 2000 also covers the session layer in the OSI model in terms of starting, maintaining and terminating communication sessions. Here's another protocol, Multifunction Vehicle Bus, part of the train communication network. There's also Smart Wire X, solving the wiring complexity for the modern racing car. There's a SPI, Synchronous Serial Interface. There's VAN, VAN, Vehicle Area Network. There are more protocols than I have mentioned. I just want to highlight, when we talk serial bus networking, it is not just about CAN. And since we are going to be diagnosing network problems, we need to be aware that there are different characteristics about the different protocols. Now I want to focus you on the four most common protocols we see in our modern cars today, two of which we have already mentioned, being CAN and FlexRay. The other two is MOST, M-O-S-T, and LIN, L-I-N. These all need to be looked at again as we conclude our presentation on the different protocols. One being LIN, L-I-N, Local Interconnection Network, a very low cost in-vehicle sub-network. In order to have a standard sub-bus, car manufacturers in Europe have formed a consortium to define a new communication standard for the automotive sector. The new bus, called LIN bus, was invented to be used in simple switching applications like car seats, door locks, sunroofs, rain sensors, mirrors and so on. The LIN differs from the CAN protocol. The LIN concept uses a single master, multi-slave modules. Only the master is able to initiate a communication through a single wire bus line. Another popular and modern protocol is MOST, Media Orientated Systems Transport, a high-speed media interface. The serial MOST bus uses a ring topology and synchronous data communication to transport audio, video, voice and data signals via a plastic optic fibre. MOST is a very efficient and low-cost mechanism for transporting high volumes of data. The MOST system is optimised for the automotive applications. It is a low overhead and low-cost interface used to communicating with a wide variety of peripheral devices in the car environment, like microphones and speakers. We may not need to know everything about the engineer's architectural makeup of the serial bus protocols and bus network systems. But in saying this, it is still wise to have a good knowledge of the design and how it all works. The layers that make up the architectural design really messed with my head as I tried to comprehend what I was reading. What do they mean? And all these layers that we have all heard that make up, say, the CAN bus protocol. I do not know about you, but when something messes with my head, I tend to want to give up. I have since learned that this is computer talk for the physical network components and the software. Why call it layers? Who knows? But I do know it is all computer talk for the physical and as well as the software engineering rules that govern the factors that make the network what it is. Now that I know this, it doesn't seem so complicated because at the end of the day it does not help me to fix the car. As a repairer, I do not see the point in going into all the ins and outs of the different layers, but it would be wrong of me not to give you a brief summary. CAN protocol has 7 layers. Physical layer. The physical layer is what we see and is a tangible part of the protocol. It is a protocol that defines the physical layers of a serial bus. The basic physical connection and wiring between the communicating modules takes place here in the lowest layer. The mechanical and electrical coupling to the transmitting medium is determined here by specifying, among other things, the cable, the distance involved, the pinning of connectors, and the way the bits are represented. Next we have the data link layer. This layer is responsible for assuring that a reliably operating connection is made between 2 or more modules. For this purpose, the protocol of this layer determines the method of protecting transmissions, the telegraph structure, methods of accessing the transmission medium, and for the synchronization and addressing of participants. It should be possible to identify the correct faults in the data link layer. Network layer. The network layer undertakes the choice and implementation of the best transmission route in a network between communicating parties and provides the service of routing to the transport layer. This function is of particular significance when different protocol networks need to be connected by means of a gateway. For example, the PCM may need to communicate to the LIN network, and via the gateway this is made possible. Now we have the transport layer. The transport layer represents the boundary between application-orientated layers 5 to 7 and the transport-orientated layers 1 to 4. Its job includes guiding the information through the network, controlling the flow of information, and the grouping of individual packages. The session layer. The session layer provides procedures for the opening, the orderly progressing, and the transmission of a communication session. Now we have the presentation layer. The data of the application are converted in the presentation layer into a data format or language which the receiving application can interpret. This layer thus implements the matching of data formats and the conversion of codes. Last, we have the application layer. Application programs which need to be developed can thus access the function of the open system via the application layer. Just on concluding on the layers, I want to bring again to your attention ISO, International Standards Organization, and also OSI, Open System Interconnection, is a standard that all computer engineers use when building network protocols. Before these standards, networking was all over the place and no real unity was present. But today we have ISO to thank for all these standard layers of the network protocol. Without these standards, our job as a repairer would be almost an impossibility. But because of the standards, all the different networking protocols nowadays have to use the same building blocks. And it is not just for the automotive industry, but a standard for computer networking systems where different nodes need to communicate with each other. Folks, we have only just got started on the bus journey, and we have hardly touched on what you, the technician, needs to be proficient in your diagnostic repairs in bus network systems. You may well be thinking what I've shared has no to little bearing on the ability to repair a serial bus system. In some ways you could be right, but let me remind you, I've only just touched on the theory side of a bus network system. This is only the introduction of this series. There is so much more to come after this video. Unfortunately, I've had to leave a lot out on this theory presentation, but it's up to you guys now to find out more on your own journey for your quest for knowledge. Remember, knowledge is a powerful tool. I'd like to leave you with some thoughts. Not my thoughts. Socrates says, "I know nothing except the fact of my ignorance." Do we want to be like that? I hope not. The Bible tells us intelligent people are always ready to learn. Their ears are open for knowledge. Proverbs 18:15. Henry Ford says, "Anyone who stops learning is old, whether 20 or 80. Anyone who keeps learning stays young. The greatest thing in life is to keep your mind young. Folks, this brings us to the end of part 1 of Serial Bus Network Systems. As we have only just started, I look forward in having you join me in part 2 and 3 as we learn more and go into the real matters of diagnosing network system problems. I know I'm not the best at telling jokes, but I felt I'd like to finish with a protocol joke. At least that was, until I realised protocol jokes have to follow protocol. One of the problems I had was finding the right frequency to tell the joke. Also, protocol jokes have to have a handshake and a password if they were to be accepted. So folks, just relax. I will no longer burden. Folks, thank you for joining us in this presentation. I look forward to having you join me in part 2 and part 3. Thank you. God bless.